Hi, my name is Amarin.
And I am Dasha Hadadeen. We are students in Princess Sumaya University for Technology.
And today we're going to solve an example in microwave engineering course. The example is a transistor that we're going to design an input matching circuit and output matching circuit for this transistor. We have the S parameters for our transistor. And we're going to solve it using our MATLAB calculator.
And Kitab, using the Smith chart.
Yes. Okay, so here's our MATLAB calculator. We input our S parameters over here. First, to find if our system is stable or not, we press on basic data.
And we check whether delta and k. We check if delta is less than 1 and k is larger than 1, then it is stable. And my circles are outside the Smith chart.
As in this example. Okay, but nevertheless, we're gonna draw our stability circles. We press on stability circle and we have the input stability circle and the output stability circle with the radius, magnitude and phase.
Magnitude is how far the stability circle is from the origin in the Smith chart, and the radius is the radius of the circle.
Now first we're going to draw the input stability circle. We have the magnitude of 1.82. So we go to the Smith chart. But since 1.82 is larger than 1, which is our radius or scale on the reflection coefficient, which is from 0 to 1, then we multiply 1.82 by, for this example, we use the calculator. Sorry, we use the
ruler, and we checked how long is it in centimeters.
Yeah, and it's 6.2 as you can see here. So we multiply 6.2 by 1.82 to get 11.28
centimeters far from the origin.
Yes. And now we're gonna have to draw this, but it's gonna have to be with a phase that is
145
as we can see here. Okay. Now if we draw it and it's 11.2, then we get this over here, which is the center of our input stability circle.
Now we get the radius from the MATLAB calculator we got before. Since it is less than 1, we don't use the centimeters, we use the scale we have underneath the Smith chart.
And it's almost 0.3. So we go to Kitab. We have our compass over here.
We open it to 0.3 on the third scale.
Yes, the reflection coefficient scale. And where's 0.3? It's almost here, right?
Yes.
Okay, now we take this.
And we put back the pen and draw our stability circle. Now we finished drawing both our circles, the input stability circle and the output stability circle.
We have the input stability circle over here, and we did the same thing for our output stability circle, and we have it over here. And as we can see, both circles are outside our Smith chart, so the system is always stable.
As we got from the K and delta.
Yeah. Now next we're gonna find our constant gain circles. Over here we calculate the maximum gain at the input and maximum gain at the output using these formulas. Using our S parameters, we find that our maximum gain is 1.37 dB at the input, and at the output it's 1.14 dB.
Therefore we can't choose any circle higher than 1.37 dB at the input and 1.14 dB at the output.
Therefore we choose 1 dB, 0 dB and minus 1 dB for both the input and output. Now to find the values that we calculated in this table,
using MATLAB calculator,
we go to our MATLAB calculator over here. We have our S parameters, we press on constant gain circles, and over here we choose our dB gain. For example, let's put 1 over here and 1 over here.
But less than 1.37.
Yeah, it should be less than the maximum value. Now we get the radius, magnitude and phase.
The same way we did our stability circles. We get the radius and the magnitude.
Now if we change these values to 0 and 0 dB, we have another values. So we took all these values and put them in a table, which is shown over here. We have 1 dB, 0 dB, minus 1 dB, and we have the radius, center, radius, and center. But before we start drawing these circles, we have to point out our maximum gain at the input and maximum gain at the output at the Smith chart over here.
With the phase, the same phase as S11,
yes.
The same. Now we pointed out our two maximum gains, one at the input and one at the output.
This one's the input and this one's the output.
We obtained these values from our S11 parameters and S22.
And S22 parameters, as we can see here, here's the magnitude and here's the phase.
With the conjugate phase.
Yeah, since we're using the conjugate of S11 and S22, we get phase 1, 45 and 20 degrees. So now we have our maximum gains over here. Now we can start by plotting out our first gain circles at the input. Let's start with which one?
With gain 1.
Let's start with 1 dB at the input, which is the radius is
0.213.
and here's the center. So we'll start by pointing out the center, which is 0.48, 0.49.
With the same phase, of course, as the maximum gain circle.
Okay, so we go to tools, compass. Now, at this scale, we said it was 0.488, so it's almost 5. It should be like this.
This is how far my center is.
Let's choose a different color for this. From here, right?
Yes.
We go to blue, for example. And this is our center. Now the radius, we find it out the same way.
0.21.
0.21, so it should be over here. Now we place this edge on the center and we draw a circle over here. This is our
1 dB circle
at the input. So let's add the text over here and say it's 1 dB.
We finished drawing our constant gain circles the same way we did for the first one, which is 1 dB. We drew another one at the input 0 dB and another one minus 1 dB.
And we did the same thing at the output for the output gain, constant gain circles. So now we have 3 constant gain circles at the input and 3 at the output.
Now we're going to talk about the gain and how to get the gain we want.
If we press on transducer power gain on the calculator and we press on transducer power gain again, we get the matched transducer gain, which is 8.16, which is the maximum dB for the transducer. And then we have the maximum transducer gain for the entire circuit,
which is 10.7.
Yeah, the way we get 10.7 is if we add 8.16 over here.
To the maximum gain we got from the S11 parameter, which is 1.37
dB at the input and 1.14 dB at the output. Now for this example, we're gonna pick the 1 dB circle at the input and 1 dB circle at the output to find our matched network at the input and the output.
Get a gain of how much?
Yeah, before we start, let's calculate the entire gain. We have 1 dB and 1 dB, so it's 2 dB. And we add it to the 8.16.
This is a fixed gain, 8.16. We cannot control.
So we get 10.16 dB for the entire system. Now going back to the kitab over here, if we zoom in at the input and output, 1 dB circles.
We picked 2 points.
Yeah, this one and this one. marked in black.
It is easier for us to go to the center.
Yeah, we picked those because they're a straight shot to the center of the
Smith chart.
Smith chart.
Which is matched.
Yeah, but the way we go there is through a constant conductance circle, which is shown in over here.
Yes, point it out in black.
I'm gonna mark it in yellow.
Yellow. Okay.
From this point, we go straight to the center at the input, and from the output, we go on a constant impedance circle straight to the input as well. Now this is our last part. We're going to calculate the matched network for the input first. If we calculate this point,
we want to know the component we used to get the matched.
Yeah, for first with this point at the input, if we go through the Smith chart, we find that it's at 0.8.
Almost 0.8.
0.8, but this is the admittance. So let's write it over here. I don't want yellow. I'm gonna go back to black. So y1 equals
0.8.
0.8, and this is over here, and we're gonna go to the other point, which is at the
output.
Yeah, and if we look for this at the red part of the Smith chart, we find that it's 1.5. Z1 equals 1.5 ohm. So as we can see, this point we pointed out as y equals 0.8, since we're going to be working on admittance, and we pointed out this point as z, since it's an impedance. Now for this point, which is y, since we're moving on a constant conductance circle, then we're adding a parallel component to the matching network, and vice versa. Since we're moving on a constant impedance circle at this side, we're adding a series component.
And since this is an admittance, since we are moving clockwise, we are adding a capacitor, and here, since we are moving anti-clockwise, we are also adding a capacitor.
And as we can see, these values 1.5 and 0.8, over here we have this the entire circuit. At the input, as we said, we're adding a parallel component, which is a capacitor, and has the value of 0.8, and at the output part, we're adding a series component, which is also a capacitor with the value of 1.5. And now we have the entire circuit. Here's the transistor with the 4S parameters. We have the input matching circuit and output matching network.
And with an overall gain of 10.17.
10.16.
Okay.
Okay. Thank you.
Thank you.
Have a nice day.